All right, good morning. Sorry about that. All right. So, I guess if this were a concert, I'd be the opening act, which you didn't all come to see because you came to learn how to program in parallel. But I'm going to give you a little bit of motivation as to why we're doing this. My name's John Kubiatowicz, but as you already heard, most people call me Kubi because they can't pronounce my last name, which is fine. Good. So it's kind of interesting to see where we've come. That was pretty good, by the way. Where we come over the past decade and a half or so. And basically what we have seen is that the world is pretty much a large parallel system. So if you weren't aware of that, you've probably been missing a lot because we have huge cloud computing facilities at the high end. And then we've got parallelism all the way down into cell phones and cars and what have you. Who knows how many processors are typically in a regular car these days? How many do you think? 10, 100,000? What order of magnitude? Now, order of magnitude almost 100 in many cases, so it's a lot. And so you might say, well, okay, so parallelism has been around for a very long time. So why was there this big push on parallelism in the 2000s and into now 2013? And the answer really is because parallelism, although it's always been kind of easy to do parallelism at the high end, it got pushed down to the low end, and that got a little difficult, okay? And suddenly the programmers of all sorts had to be much more aware of parallelism even in their applications. Up on the high end here, of course, you get parallelism just because there's many people doing the same thing, and so you just get parallelism just by many requests. But once you get down into the low end, you got to do something else because each individual application has to be parallelized in some way. So this has gotten a little tricky. And another thing that hopefully you haven't missed is that Mini-core has arrived. Okay, way back in 2007, it's hard to believe this is 5 years ago now, Intel had an 80-core experimental chip that they produced that it had a couple of floating point engines per core. It actually had a mesh-like communication network, 100 million transistors. And, what was interesting about this was really the number of processors that they just sort of shoved on a single chip. Okay, and then they had a follow-on, which they called the single-chip cloud computer in 2010, which had less processors, but maybe a more interesting communication infrastructure. And so I don't know if any of you have purchased any sort of cell phones or computers in the last 5 years, but you probably couldn't avoid sort of deciding how many cores you wanted, right? That's just kind of a standard thing. And so the natural question kind of comes into play, what do we do with all these cores? So first of all, when I say mini-core, what do I mean? Well, let's be optimistic. I'm kind of talking maybe 64, 128 cores. When we started the PAR lab, it seemed like we were destined to go there very quickly, and for various reasons, including the fact that these things have been a little bit challenging to program. We haven't quite reached there on a regular basis, but there are chips out there with 64 cores on them. How do you program this? Well, you got your laptop. It's it's got 80 cores on it. What do? Well, you use 2 CPUs for video and audio. You have one for a word processor, one for your browser, 76 for virus checking, right? Or maybe you're using one of these to text or something. I don't know. But clearly, this is not where we want to be. All right. Now, one might argue you need several for virus checking, but you certainly don't want to be using the bulk of what you got. And so something new is clearly needed, and that's where the PAR lab kind of came into play, and other people who have been interested in parallelism. So what I want to do is today, to get you prepped for this interesting programming experience, is pick up some common terminology and concepts for later in the course. I'm going to start by giving you a little bit of a history lesson in some sense about parallelism, uniprocessor parallelism. And it was the case before the turn of the century that computer architects were very optimistic that they were going to be able to hide parallelism entirely from programmers. And, you know, what happened was we were on this wonderful doubling of performance every 18 months, sometimes called Joy's Law. And, you know, I'm going to tell you kind of what they were doing and why they ran out of steam. Okay? And then that leads us into parallel computer architecture. So the moment you can no longer hide parallelism from programmers, now you suddenly have to deal with things like programming models and shared memory and synchronization primitives and message passing and so on. So we'll give you a little bit of a flavor for that. And assuming that we have some time at the end, I'll do a quick pass through a zoo of some parallel machines just to let you guys see what's out there. Okay, any questions on our plans for today? Okay? All right. So let's start with a little bit of computer architecture. So the first thing I want to mention is computer architecture is really not just about hardware. If you thought it was, then hopefully I can convince you otherwise. But if you look at what a program is, today is the programmer writes something. It often goes through a bunch of source-to-source transformations, changing it from one language to another or supplementing whatever language you're writing in. Then it goes through a compiler. Then it's linked with a bunch of static libraries and some stubs for dynamic libraries. And then you get a binary out of it, which then tries to run on the hardware, which has dynamic libraries in it and OS services and maybe running on top of a hypervisor. And oh, by the way, the hardware is down here somewhere. Okay? So the stack of what it means to run something on hardware really has to include the whole piece here. Okay? All of these aspects. And I like to think of this as the VAX fallacy. The VAX architecture was extremely popular for a long time. And in its heyday, the notion was kind of we're going to produce one hardware instruction for every high-level concept. And my favorite absurdity in that was really a generalized polynomial multiply instruction, where you'd set up all the parameters for the polynomials, and then you'd run one instruction and it'd multiply the two polynomials together and give you a third polynomial. Okay, now, does that need to be done as one instruction? Probably not. You could probably do it much better by making faster, smaller instructions. Okay? And that's really, this kind of situation arrives when you're really not looking at the whole picture. And so this is kind of what I like to think of as the RISC philosophy, which is a full systems design looking at the whole picture. Hardware mechanisms are really viewed in the context of how they're going to be used, in the context of a complete system, and cross-boundary optimization really being of interest. Okay, and this philosophy has really come back again strongly when we get into the parallel realm, because there's been a zoo of different parallel architectures out there, and you really have to be aware of the full context in which things are running in order to make things run well at all. And so the modern programmer does not see assembly language unless you're a very specialized programmer. Many of them don't even see low-level languages like C. How many people here are Ruby programmers or some other high-level language? Okay, we have Java, sure, why not? Yeah, C++ is getting pretty low-level, but things that have garbage collection in them are probably pretty high-level. But I'm thinking really high-level are like Ruby and Scala, some of those. So how many people here are C programmers? Let me just ask. I'm kind of curious. Okay. Maybe that fits the interest here. So there's more of you than I would have expected. Now, do you prefer to how many people prefer to program in C over all other languages? Or C++. Okay. We have some good diehards in here. I like that. So what is the not fooling yourself? So this is strictly right out of sort of the standard computer architecture text, which is you sort of have this triangle of cycles per instruction, cycle time, and instruction count. And the amount of time a program takes to run is really the product of instructions per program, cycles per instruction, seconds per cycle. And you can kind of see that all the different facets, like the program may impact how many instructions are used, the compiler might impact the instruction count, or which instructions, whether they're high or low CPI, and so on. So really, how do you make something fast is not just about necessarily even reducing instructions all the time. It's more about the whole optimization. Okay? So this is the don't fool yourself in the shower equation. This is the really don't fool yourself in the shower equation. How many people know of Amdahl's law? Okay, so Amdahl's law, roughly speaking, is a way to look at what you're actually speeding up. And I think graphically what I show here is pretty easy. Here's a program where the green part is something I have some control over, and I might speed that up, but I don't speed up the red pieces. And if you look at the total program, has not sped up as much as you think, even though the green piece is sped up by half. Okay, and in fact, the way I've got this set up with a third, a third, a third, suppose that that green thing is infinitely faster and therefore takes no time. I've still only sped things up by what fraction? Okay, so it's 1.5, right? So this is 3 over 2. So this is, got to be careful. It's oftentimes you're sitting in there, you're thinking, and you're saying to yourself, gee, I could make that thing infinitely fast. Isn't that great? Well, you better make sure that it matters, right? If you make a little thing infinitely fast, it doesn't help you all that much. And this is really easy to get into when you're programming in parallel, because you might get the parallel section to be extraordinarily fast, and it doesn't matter because the serial section kills you. Okay, so always be aware of what you're spending your time on. All right. So let's talk a little bit about universal parallelism, or uniprocessor parallelism, I mean. So parallelism is everywhere. Modern processor chips have about order billion transistors. So clearly, if we were using each of those transistors in series, we're not doing anything. So we have a billion things. We hope that some of them are working in parallel. Okay? And the question is really not whether they're working in parallel or not, but how much of that parallelism does the programmer need? Now, of course, there's another interesting problem here today, which is what? If you've got a billion transistors and they're all running at the same time, what happens? You probably melt your chip. Okay? So you got to be very careful about which transistors are running when. Okay, so we'll talk a little bit about that as well. So how do uniprocessor computer architects get parallelism? So they basically find parallelism within instructions. This is called instruction-level parallelism. And the theory here is to hide the parallelism from the programmer, and I'm going to tell you a bit about where this ILP might come from. And so, in particular, the goal of computer architects until about 2002 was really hide underlying parallelism entirely from the operating system, the compiler, and the programmer, because they could. Okay, why give complexity to a programmer if they don't need to think about it? And this led to a kind of an interesting philosophy of programmers, which was, oh, my thing is too slow today, but, well, I'll wait for the next generation, it'll be fine. Right? There was laziness on the part of programmers because they could wait. All right? So much for that. We'll say a little more why. So examples of ILP techniques are things like pipelining, which is overlapping individual parts of instructions, superscalar execution, which is doing multiple things at the same time, VLIW, which is letting the compiler say what things run in parallel, vector processing, which is specifying groups of similar independent operations that have a lot of similarity with vector mathematics. Out-of-order execution is basically allowing things to be executed in different orders than the programmer specified them to get performance. And I'm going to touch on each of these just so you have a flavor for them. Okay? Questions? By the way, feel free to ask questions. I can almost see you guys out there. I got the light shining in my eyes. But so let's start with parallelism. So this is one of my favorite Dave Patterson slides. I used to use this in undergraduate computer architecture classes all the time. And this is a good idea of what pipelining is. Okay, which is you have a situation here where you need to do a bunch of loads of laundry. You're going to wash some, and each wash takes 30 minutes. A drying takes 40 minutes, and folding takes 20 minutes. And so if you were to do a load sort of straight through, it would take about 90 minutes. And so the question is, how do you really do that laundry? Well, you don't do a single load at a time. You try to use parallelism, of course. You try to have a situation like here where you're folding the first load, drying the second, and washing the third, obviously. Okay? Anybody who's ever been an undergraduate and had to deal with laundry. And so if you look at this sequential example here, it would take you 6 hours if you did everything one at a time. But if you pipeline it, you end up with 3.5 hours here. And the reason that this is not 2 hours is that, in fact, these stages are not all the same length. We have 30 minutes, 40 minutes, 20 minutes. And when you pipeline, you're kind of forced to go with the slowest stage. Okay? All right, this is all pretty simple. So pipelining helps the bandwidth number of things we get per unit time, but not the latency of an individual load. Bandwidth limited by the slowest pipeline stage. And in the best case, the speed up is the number of pipe stages. So if these were all equally 40 minutes initially, then I'd get a speed up of 3. Okay, pipelining. Now, of course, you can use pipelining as much as possible, but there are some limits to pipelining. So for instance, maybe you could split the wash into the soap up and rinse pieces. So, it's soaps, and then you take it out of that and put it into the rinser. And as a result, maybe I get more stages. I guess the dryer now needs to be split into get most of the moisture out and finish it or something. I mean, we could try to split these stages finer and finer and get more parallelism. But as you can see, there's some things that get in the way there, right? Like overhead of switching pieces from one thing to another. Okay? Now here is the classic 5-stage pipeline. This is the MIPS one, but it gives you an idea what a processor might do for pipelining, where one stage is fetching, the next is decoding. So fetch the instruction out of memory, decode the instruction to figure out what it is and get its arguments, actually execute the instruction, do any memory operations that are the end, like writing back to memory, and then finally writing back to registers, and so that ends up being 5 stages. All right? And here's another way graphically to look at that. So here I'm showing kind of the instruction fetch, the register lookup and decode, the execute, the memory stage, and the register write back. And the blue is that we do the register lookup on the second half of the cycle and write back on the first, but no worries there. How many people have seen a pipeline like this? Okay, a few of you, good. So basically, in the best case, we could get one instruction pumped down this pipeline per cycle. Okay, and superscalar is more than one instruction per cycle. Okay, so these are kind of simple terms. Now, unfortunately, this sounds great, but in addition to the overheads of splitting things into finer stages, we start running into hazards. All right, so what are some limits? Well, first of all, the overheads, as I mentioned, prevent arbitrary division. At some point, the cost of the latches, that's these green things here, outweigh the cost of the stage, and so that kind of prevents you from going arbitrarily small. And also, hazards are things like structural data and control hazards. So a structural hazard basically says, well, I'm trying to use the same item by 2 instructions. So clearly, I have to serialize when I only have one of something. Like, for instance, maybe I've got 2 instructions and they're both trying to simultaneously use part of a floating point unit. Well, those 2 instructions can't run at the same time. They've got to run separately. Okay? What do you think about structural hazards when I've got a billion transistors? They're going to stick around or not?
No.
It's easy to get rid of them, right? Because if you don't have enough of something, just add some more. Okay, so structural hazards are often not our biggest problem here when we've got a billion transistors. Data hazards, which I'm going to show you in a moment, are interesting. These are when instructions depend on the result of a prior instruction. I'll show you that. And control hazards are really a big problem because this is a case where I'm about to branch. I'm going to make a loop or something, and I've got to decide before I know the result of the branch whether to branch. It's called a control hazard. And the best I can do in many cases there is guess. I think I'm going to go back. Okay. Right, it's called branch prediction. So data hazards and control hazards are tricky ones. And superscalar, the more instructions I get going in parallel, kind of the more hazards I have. So you can start to see where some limits go into play. So here is an example. This is a fairly standard kind of assembly language syntax in which the destination register here is on the left. And what I'm doing here is I'm loading from an address into R1, and then I'm subtracting from R1 minus R6 to R4, and R1 minus R7 to R6, and so on. And if you look here, notice that the value coming out of memory has to go kind of backward in time here to the ALU in that first case. So that's why I'm marking it as red. Okay, because this is a single time slot here. So in order to go from memory to that ALU, I would have to delay everything. All right, so that's a red hazard. The green case here, I can go from a load down to this ALU. That's not a problem because that's forward in time. And then finally, by the time I get down here, this value is already in the register, and I can go from this register file to that, and there's no hazard. Okay? So, you know, if you're not catching all this right now, that's fine, but the basic idea is when I have a lot of things going in parallel, I have to worry about whether something in one stage is needed by another instruction in another stage. And I've got to be very careful to do all my accounting so that when I'm done with all this parallelism stuff, I still get the right answer out of it, and it still fools the programmer into thinking that everything is happening one at a time, because that's their mental model in this. Okay? So I have to fool the programmer into thinking, yes, a value loaded into R1, and then R1 was used in the subtract, and R1 was used in the AND, and R1 was used in the OR. Because if I don't get that right, I'm in trouble. And this is where, if you're a computer architect and you love computer architecture, this is kind of your bread and butter. You have to start worrying about data dependencies inside the hardware. Okay, and I'd be more than happy to talk to you guys a lot more about this in detail afterwards. But the net result of this is, how do I fix this data hazard? Gotta wait, right? The best I can do here is, yeah, I got it out of memory and I stall everything one cycle so that this arrow is now forward in time. I mean, so you fix data hazards by waiting. And you got to do it cleverly, because if you wait too much, you lose all the advantages of parallelism. All right? I once had a Greg Papadopoulos, while he was still at MIT, once gave this amazing lecture that I remember well, where it was a computer design class, and he got up there and he said, today we're going to talk about a new type of logic, FTL logic. And he sat down, he was deriving the properties, and he got kind of halfway through the lecture, and then the fact that it got the output before the inputs were available, you started wondering what's going on here. And then by the end, he sort of told you, yeah, this is faster than light logic. Okay, it got its answer before the inputs. If one of you guys know how to do that, by the way, that would be great. That would help computer architecture a lot. But for now, we actually have to wait. Okay? So superscalar gives us more trouble. All right, any questions on the basic hazard idea? I'm not going to go into this in any more depth. Are we good? So this, you can start to see, gee, if I want to do lots of parallelism, I want to do a whole bunch of pipelining, but now there are more hazards which are causing me to wait. So there's a trade-off period there. Okay, and the more parallelism I've got, the more power I'm burning, and I may or may not be using it well. So I have to be a little bit careful. Okay? Now, what about out-of-order execution? So this is another thing that people did a lot of, still do. And the idea here is allow instructions that are fast behind slow instructions to go forward. So here's an example where I have a divide that's busy producing a value in F0. And I'm going to use that value in this add instruction. And this subtract instruction has nothing to do with either. Okay, how do I know it has nothing to do with either? Well, these F numbers here are the registers, and notice how F12, F8, and F14 have no overlap with anything in here. So basically, I could compute that subtract completely in parallel with the divide and the add, and it wouldn't cause any problems. Everybody see that? Okay, and so, gee, wouldn't it be great? Normally, if I have to do everything in order, I'd do the divide first, I'd take a long time, then I'd do the add, then I get around to the subtract. Wouldn't it be nice if I could get the subtract coming early and running in parallel with the divide? That would speed things up a bit. Okay? That's called out-of-order execution. And out-of-order execution leads to things completing out of order, which leads to all sorts of interesting problems in terms of what happens if there's an interrupt in the middle of this. And so one of the big issues is assuming that you can do this reordering and keep all the accounting right, then you got to start worrying about what happens if you interrupt in the middle here? Like, for instance, what if the divide gets a divide by 0 and I've already executed the subtract? Okay, that's now the twilight zone, because there's no place I can stop this program and say it's got some consistent value, because I've already messed up F12, but I've got a divide by 0 error here. There's nothing I can do. Okay, and so there's a lot of work that people did in terms of getting precise interrupts, which says, well, even in that funny scenario, I'm going to unroll the subtract in a way that allows me to stop here at this divide and look like the subtract never happened. Okay, so now you can start thinking, I don't know if you guys have ever had any database classes, sort of think of undoing a transaction almost. Okay, but this is in hardware. Okay, the reason I'm giving you this is to get to a flavor of what actually is happening in some of these modern chips. Okay? And so another thing you could imagine here is if these instructions also all take different amounts of time, then we can start getting some interesting things here where this multiply is taking a long time, And it's going to be input by, so multiply is producing F0. It's getting input to this divide. I have to make sure this divide waits long enough before it starts so that it actually gets the value it needs. That's called a read after write hazard. Okay? If I start this divide early, I'm going to get the wrong answer because the multiply is not done yet. Okay? And this is a more interesting one called a write after read hazard, where I've actually altered F6 early, and the divide hasn't read it yet because it hasn't started, and so I get the wrong answer. Okay. We're not going to go into any more detail than this, but I just wanted to give you a flavor of the interesting types of hazards that somebody who's gung-ho and they're going to make all of the instructions that the programmer gives them, reorder them, run them out of order in a way that is the best possible execution to try to make them go quickly. They have to think about a lot of things, and they have to do a lot of accounting. So here's one way to do the accounting. So this is the basic Tomasulu architecture. Came from IBM way back when. You might be asking yourself, how do I make all this work? Well, what's cool about this is the idea here is that each functional unit, like an adder, has an input queue called a reservation station, and this reservation station basically holds the instruction until both of the operands are ready to go. And let's suppose that this adder is going to use a value from the multiplier. What happens is I put the instruction in one of these queue slots. Maybe I have one value already out of the register. The other one I put as a tag, say molt1, which says, well, when molt1 finishes, the result gets broadcast, comes to my reservation station, and then suddenly I've got everything I need, and now that add can fire, and I can run the fire. I can run the add. So this basically sets up a data flow by tagging results, and so this sort of execution engine will run everything out of order, but still meet the data flow because I tag all the instructions I need results from by the names that they're going to produce when they're done. So I basically take the input stream, turn it into a data flow graph inside. Okay. So, how do we get ILP in a modern situation? Dynamically scheduled out-of-order execution. So current microprocessors might fetch 6 to 8 instructions per cycle. Poof. Pipelines are tens of cycles deep, many overlapped instructions, all in execution at once. Okay? What happens? Ready for this? Everybody listen. Grab a bunch of instructions, determine all their dependencies, eliminate dependencies wherever possible, throw them all into the execution unit, let each one move forward as its dependencies are resolved, make it look to the programmer like it all happened sequentially and didn't happen out of order, and then you win. Question? No. So that's a tall order. It's actually kind of fun, right? If you want to take a computer architecture class that teaches you how Tomasulu actually works, I support that. All right, that's bread and butter. Good stuff. But here's one last interesting thing, which is you may actually have to guess because you've got all of these long pipelines and many things in parallel, and sometimes you need something long before it's done. What do? You guess. Okay, you might speculate on branch results, dependencies, even values. Oh, I need that value out of that register. What is it? I'm going to guess that it's 4. We'll start executing. Now, what if you're wrong? Well, you got to have a way to unroll. Okay, and so there's a lot of this speculative execution that goes on. And a downside of speculative execution, which, by the way, is the bread and butter of the higher-end processors that we have pretty much everywhere. You get an x86 processor, you get something from AMD, you get something, anybody that has kind of powerful execution engines, they're all doing this speculative execution. And the danger there is that if you speculate too much and you throw out too many results, you're burning power and not getting performance back. On the other hand, if you're doing a reasonably good job of guessing, then it may be that you can guess and get ahead of the game. It's a trade-off. Now, you might ask yourself, how good can this guessing be? And it turns out that actually guessing rates in the 95% or better on branches are not uncommon. So branches are pretty good to guess at. Okay, to the point that it makes absolutely no sense, if you don't care about power, to run both sides of a branch and pick the one that's right. That's just wasting power because I can do a better job of guessing which side to go and only doing the one I guess. Okay, and I'll get, as pretty much indistinguishable performance from doing both sides. Okay. But of course, there's a huge complexity. And many of the components scale as n squared, where n is the number of issue instructions. Question, yes? Well, how could it guess something like a branch, for instance? So, surprisingly, computer programs are very regular. Think about a loop for a moment. Okay, if you loop for 10 times before you exit, and it's guessing that you're always looping, you've only got kind of a, you lost once out of 10. That's 90%, right? And that's a non-sophisticated branch predictor. So it turns out actually that people have studied the regularity even in data patterns, like the loads in a loop, oftentimes maybe 0 or something. You think of a poorly optimized sparse matrix algorithm where there's a lot of zeros. Okay, now Jim, who was up here earlier, is shuddering in the wings. He would never do that, but you can imagine there, because he's much better at sparse matrices than that, but you can imagine that there's a lot of predictability even in the data values. People have had less luck, by the way, with data than branch prediction, but branch prediction is used everywhere, and there are decades worth of branch prediction papers. So, any other questions? Go ahead.
It seems to me you mentioned earlier that there's a whole stack of software hardware.
Yes.
Would compilers deal with a lot of this as well?
So that's an interesting question. So the trade-off of how much the compiler knows that's going on versus how much the hardware hides, it's an interesting trade-off there. And partly, in principle, if your architecture's never changed, the compiler could do a lot of rearranging in interesting aspects. And in fact, usually compilers that come out of Intel for Intel processors or whatever, they know enough about the architecture to do a reasonable job of putting the instructions in a way that the hardware will find the parallelism better. However, you still want a lot, by the way, here's a party line. You still want a lot of hardware hiding of at least the parallelism, because when you change an architecture from A to B, the latencies of the instructions change and all that sort of stuff, so that a program compiled to perfectly run on architecture A, Sandy Bridge, then when you get to the next one, doesn't work as well. Okay, and so 6.5 of one, half a baker's dozen of the other, I think, on that. So it's an interesting thing, tricky. But yeah, you're right. Given what I said earlier, you'd like the compiler to know as much as you want, and it's really a trade-off of how quickly you change your architecture. Good question. Any other questions?
Actually, as a follow-on.
Sure.
What about Java just-in-time compilers?
So just-in-time compilers are compilers that are basically just making use of runtime information to do a better job of optimizing. So they're kind of in almost the same position I just mentioned for a regular compiler, except they have a little bit better information about what data values are actually going to be there. And so, just-in-time compilers, you could have trade-offs behind how much they know about the hardware and how much they don't. Usually they're getting a lot of benefit, though, out of the data values. Gee, look, this really is 0, therefore I can get rid of this whole branch of the code. And so that's when just-in-time compilers are doing a good job. That's because they're doing data-dependent optimization. Not so much because of the hardware underneath, but they do some of that. So let me just give you a good example of a pipeline here. What are we talking about? So here is an old school. This is from a decade ago, but it's good to see. Superscalar and out-of-order execution engine. So here we have the instruction fetch branch predict loop, and notice how this loop is independent of the rest of the execution engine. That's because of branch prediction. So basically this guy is chugging along, predicting what instructions are interesting, and they're dumping them down this multi-stage instruction crack and group formation section. So this is doing decoding on many stages, and then you have several execution units, some of which handle branches, some of which do loads and stores, some of which do floating points and others. Okay, and so the properties of this particular chip way back when was 8 execution units in the out-of-order engine. So there's actually 8 units here. In-order instruction fetch, so you fetch everything in order. And the reason we fetch in order and execute out of order, can anybody guess? So I always grab the instructions in the order the programmer originally intended, but then I mix them all up once I execute. What would be the reason for that? The reason I have to take things in order is I have to figure out what is the data flow from instruction to instruction that the programmer intended for correctness reasons, right? So I sort of, it's like I'm scanning through in order when I'm doing this fetching, and then I'm building this internal data flow graph, and then I can run things out of order after I've figured out what the dependencies are. Okay? And then, of course, in order to get a nice, precise exception at the end, we reorder things so that they only commit back to the register file in the order that they were intended by the programmer as well, and that's kind of how we get this unrolling aspect. Okay, so, all right. You guys still with me? Now let's take a look at some amusing data. Here is simulation data. This came out of the University of Washington way back in 1995. And it shows an 8-way out-of-order execution engine. And what you want to see here is here's a bunch of benchmarks along the bottom. And this is the percent of the total cycles being used for something. And this is a breakdown on each of them. And the most important thing you ought to see is black. Okay, black is actually useful instruction cycles. Okay, everything above it is non-useful overhead, like speculative executions that were thrown out, waiting on a unit that's producing something you need. All of that, you can go through all of these. Floating point units that take a long enough time that they're holding other people up, and so on. Go ahead, question.
So why are the processor busy important?
So processor busy actually represents having committed real results. You're actually having made it through and done something useful. Okay, whereas the rest of this stuff is, I don't want to call them wasted cycles, but they're cycles that didn't end up ultimately giving you a result. Okay, it's overhead. And the interesting thing to note about this is once we get out to 8-way trying to run instructions 8 at a time, we get a lot of wasted overhead. Okay, and so this is kind of, you can start to see the cracking in the ice, right? Because I could spend a lot of my transistors doing an 8-way issue, but if I'm only getting 20% utility out of that, then maybe I'd have had less instructions per cycle and sort of less wasted stuff. Okay, and so this up here you could almost argue leads to power that it wouldn't be wasted in a, say, a 5-stage pipeline from way back when. Okay, and so people who said, oh, parallelism, yeah, if we're going to go to massive parallelism, forget all this stuff, we're going to go to small 5-stage pipelines and we're going to put 1,000 of them on a chip. Okay, 1,000 5-stage pipelines versus a smaller number of big out-of-order execution engines. Okay, now which one do you think has won the generalized award here? Small number or large number? Small number of complicated or large number of simple? What?
The third one?
Third one. Oh, only 2 options. Which is the third one?
I thought talking about the choice.
Yeah, so there is a third option here. I would say the one that has won, if you look at all the Intel processors and so on, has pretty much been smaller number of complicated processors. Okay? And the reason is that parallelism is hard to get to work well, and this, even though you've got this overhead, this processor still speeds up your serial execution stream a lot better than it would if you had a bunch of little tiny processors all trying to run your program. And think about Amdahl's law, right? Amdahl's law says, another way to look at Amdahl's law is that the serial section, the part you can't parallelize, is a thing that's going to get in the way. Okay, and so it's these big processors that have tended to stick around because there's a lot of serial sections still. Okay, now hopefully today in this class you guys are going to learn how to get rid of all the serial sections and we'll get rid of that. Not going to happen. But even in the programs you're writing today and parallel and tomorrow and what is this, Friday, how long this goes, you're still going to have serial sections, and so these big processors have a tendency to be in there because they help with the serial section. Now, it may be that you want to have a bunch of 4-way out of order issue instead of 8-way. That might be a better use of power. Or the third option, which I thought you might be alluding to, is sort of mixed. A few big cores and a lot of little ones. And this is starting to show up in cell phones, actually. So there are cell phones out there now that you can buy that have 4 really big processors and one little tiny low-power one, or one big one and some small ones. So that's this mixing, this hybrid of types is starting to show up. And the reason is the smaller ones are much more energy efficient if you can use them, and the bigger ones are good for performance if you can't do things in parallel. Okay. Let me go through this and then we'll take a brief break. So let me just say a little bit about trends. So I can't possibly stand up here and not say Moore's Law once. There, I said it. That's a requirement of any computer architecture lecture. And Gordon Moore did this most amazing thing way back in the 60s. He was at a conference and he was asked, so, all right, how many transistors are really going to be on chips? And as any good academic type does, he plotted a couple of points on a log linear scale, drew a line, and said, well, it's going to do this. Plotted into the indefinite future. And that log linear plot here basically meant that he was saying that the number of transistors on a chip is going to go geometrically. It's going to double every so often, where often is small. And in fact, surprisingly, that happened. So the number of transistors on a chip were essentially doubling every 1.5 years for a long time. Okay, and he basically predicted that. Just wrote down a few dots. There's his graph. Okay, that's pretty cool. Now, transistors are only good if you can use them. And by the way, this is not performance. This is number of transistors. Okay, so Moore's Law is about number of transistors. Repeat after me. Moore's Law is about number of transistors. Okay, this is not Moore's Law. Okay, but this is a good graph from one of the recent Patterson-Hennessy books. And what this is plotting is performance over the course of this time. And what's interesting here is for several decades, or a couple of decades, we actually had 52% per year improvement in performance, which translates to about a factor of 2 every 18 months or so in performance. All right? And then, by the way, this is called Joy's Law. Remember that one? Joy's Law, okay? And then somewhere in 2002, look at the blue curve. Poof, we fell off. And notice that here's a projection. Gee, if we had stayed on our projection of doubling every 18 months, we are basically 3x behind the game already by 2006, and this has just gotten worse over time. I just only have this graph for now. So this is why you guys are here today. Okay? You could no longer get lazy and just wait for things to double, because all of a sudden, the individual processors are no longer gaining performance rapidly. Okay? Now, this is basically a sea change where we suddenly had multi-core, okay, and or many-core. And what's kind of interesting is this graph, which I love this graph. This basically shows you if I had followed the Moore's Law curve of transistors and I kept running every one of those transistors all the time, notice that here's what happens. Sort of in the 2000s, the power density is about the same as a hot plate, and then a nuclear reactor, and then somewhere up here a rocket nozzle. So imagine that laptop on your lap might be a little bit uncomfortable. All right, and so basically trying to use all those transistors, even though Moore's Law gave them to you, really started dropping off in usability because of the power that was getting taken and the subsequent heat. Okay, and so here is a graph from Stanford. And if you look here, what you see is the chip density, which is Moore's Law, kept increasing. That's great. But you see all of these things tailing off. You've got clock speed tailing off. Okay? If you were buying computers over the last decade and a half, what would you see? 100 megahertz, 200 megahertz, 400 megahertz, 800 megahertz, 1.1 gigahertz, 2 gigahertz, 2.5 gigahertz, 3 gigahertz, 3 gigahertz, 3 gigahertz, 3.1 gigahertz. Clock speed is just tailed off, right? Because it's gotten too hard to make them faster for lots of reasons. Capacitance, many reasons. Instruction level parallelism, you saw that, right? The little black piece down there is 20% of all of that time. So you just can't do more in parallel. That's tailed off. And this other one, which is interesting, is power has tailed off at 100 watts. Why is that? Well, both because you can't plug in a nuclear reactor running your computer, but also 100 watts is about the comfortable amount that you can do with regular air cooling, so on. Okay, so they basically tried to keep these at about 100 watts because that's standard heat sinks. You can go above that, but it gets really hard to get the heat out for anything higher than that. Okay, let's take a break. Let's come back in about 5 minutes or so, or maybe let's make it 7. Come on back. Get up, stretch your legs, run to the bathroom. We'll restart a little bit before 10:30. Yes.
So I didn't conclude the lecture with one section. It's like when you say sometimes you may prefer many small processors instead of a really big IC one.
Yeah.
So what's that situation?
So if things really run well in parallel, and you can really program it in parallel, then lots of small ones, you can have 1,000 small ones, and they will not be wasting power doing speculative execution and so on.
Yeah, but then if you have a lot of sequential one, then you want a really big one to actually do some branch
Yeah, because the big ones are better at taking instruction level parallelism within a single stream, whereas in many little ones, you've assumed that you have many streams each running in parallel.
Oh, okay.
And so ideally you'd have a mix. You'd have a bunch of little ones and a smaller number of big ones, and that's starting to show up.
Okay, yeah, thanks.
Sure. right, everybody come on in, sit down. Let us continue. So, the demise of parallelism at the uniprocessor level wasn't really a surprise to people. They knew it was kind of coming. And so there were many forays into ways of basically relaxing the sequential model without necessarily having to fool the programmer or tell the programmer about it, but maybe tell the compiler about it. Okay, and so one example of this is what was often called VLIW. Okay, this was, in fact, around for quite a while. Very long instruction word is what that stands for. And the idea behind VLIW was really that, well, our instructions are going to have many operations in them rather than a single one. And basically, these operations are, by definition, supposed to be independent of each other. So the compiler had said, well, here, operation A, B, C, D, E, F, G are all things that you can run in the hardware independently without having to worry about forwarding information from one point to another in the short term. Now, so what we're really saying is we're relieving the hardware from this task of trying to do that data flow analysis, which gets pretty complicated pretty quickly, and instead we've got kind of much simpler pipelines here that just sort of work their way through. The compiler has already figured out that there doesn't need to be any forwarding. And so each instruction has explicit code, coding for multiple operations. There are many different words, so the very long instruction word is kind of the simplest one, but in Itanium, Intel called it a packet. Transmeta, they called them molecules with atoms in them, so you see lots of different words here. And each operation slot is for a fixed function type, so notice we have integers and floating points and memories. Those are all separated. And constant latency operations are there. So if I do a floating point operation of a certain type, I know it'll take exactly 3 cycles, what have you. And this is all getting toward letting the compiler know what it can do. And the architecture kind of says, all right, I'm going to require the compiler to make sure that parallelism within an instruction has no read after write hazards, or there's no need for the hardware to figure out how to forward information from one to the other, and no data use before the data is ready. So if this thing takes 3 cycles, I'm never going to put a use of that value until 3 instructions later. So it's sort of, here's an example where the compiler has to know a lot about what's inside. And special compiler support has to now extract parallelism, prevent the hazards from affecting the results. And, of course, the downside of this, which came up earlier, is that in this case, since the compiler has so built its program based on a hardware description, we have to make sure to recompile when there's a new architecture because we might actually get the wrong answer if we don't. Okay? So that's important. So this is very static in its sense. So now, let's take a look here. Here's a simple loop where we load something into a register, we add something to it, and we store it back. So think of this as adding 5 to every element of a vector, or adding some number to every element of a vector. And the way we could do this in VLIW is, first of all, we put a bunch of loop pieces, unroll them so that there's many loop iterations simultaneously in here. And so now notice how here we take, we load value from the first element, and we simultaneously load from the second element. So 0 off of R1 is one element, minus 8 off of R1 is another one, minus 16 is the next, minus 24. So there's actually, 7 simultaneous iterations going on here. And now I load. I know that it takes 2 cycles for the load to happen, so I wait 2 instructions before I do my adds. So notice how the load into F0 shows up here into an add of F0. Okay, and then I do the store back after the add is done here. All right? So basically, that's one iteration where the compiler has laid this out explicitly, knowing exactly how long the loads takes, the adds, and the stores. All right? And so I've unrolled it 7 times to avoid delays. We get 7 results in 9 clock cycles. And, we've got parallelism. Woohoo. Now, notice, what do we see here? Space. Okay, so one thing you can see sort of starts to show up in VLIW architectures, which is kind of one of the things that really caused them problems in the early days, is all of this wasted instruction slots. Because in that first instruction there, I can do 2 loads, but I don't have anything else to do. So I'm wasting 3 potential issue slots. And worse than wasting 3 issue slots, I'm also wasting this space in memory. Because this instruction basically has a bunch of no-ops in it, because it's a long instruction, and I have to say, do load, load, no-op, no-op, no-op. Okay, and so this tends to blow up and be large, okay? And so that was a much bigger deal when memory was expensive, but it also causes fetch bandwidth. So there's some disadvantages to this. Okay, here's one of my favorite examples of a very tight software pipelining. This one actually works, believe it or not. Same architecture I showed you. Look, I load minus 48 off of R1. I go 2 cycles around, and then I add F0. So I load it into F0, go around, add F0, and go around one more time, and then store the F4. And notice, having gone around twice, I've subtracted 48 off of R1. So minus 48 plus R1 is the same as 0 plus R1 by the time I've gone around twice. So this particular very compressed coding actually has 9 iterations of the original loop going on simultaneously in a very tight loop. All right? There'll be a test later. You'll need to be able to understand this particular example, but you can start to see how the compiler can do some pretty amazing compressions of things when they know what's going on. Okay? So how do we relax even further? Well, now we start changing a little bit the model we give to the programmer. Okay? So here is an example of some C code, since there are many of you out there that are happy C programmers. And the goal here is, add A of I and B of I and put it in C of I and do this 64 times. And the scalar code for this would look something like this. Here's a load, 0 off of R1 into F0, 0 off of R2 into F2. So basically R1 and R2 are pointers to vectors A and B. Add them together to F4, store F4 back into 0 off of R3. So that's doing the C of I. And then I do a bunch of subtracts on my indices and my count, which is R4. And assuming I'm not done, I loop back and I do it over and over again. I do this loop 64 times. Okay? Everybody loves assembly language, right? This is probably the only course in a long time you'll get stuck staring at assembly language. What is the vector version of this? Well, look, I load my vector length 64 into the vector length register. I load a whole vector of elements into vector 1. I load a whole vector of elements into vector 2. I add vector 1 and vector 2 to get vector 3. And I store vector 3 out to R3. And I'm done. Now, what have I done here? So what I've done here is, first of all, I've added vector instructions to the architecture. But secondly, either the programmer or the compiler has to figure out that what I'm doing over here is a vector operation and to code things using vectors instead of this scalar code. Okay? And so because the compiler or programmer has said, well, these are really vectors, what the compiler or programmer has asserted in this instance is there's absolutely no overlap between independent elements here. So A of 0 plus B of 0 equals C of 0 is completely independent of A of 1 plus B of 1 equals C of 1. No dependencies. And therefore, the hardware gets a much simpler description, 5 instructions, and has a much simpler expression in the hardware itself. I'll show you in a second where it can really take advantage of that parallelism. So I've expressed the parallelism down in the hardware. Okay? And so many multimedia and HPC apps, all natural consumers of vectors. Okay? And so what's the vector programming model? In addition to the standard scalar registers, there's a bunch of vector registers. Okay, what's a vector register? Well, a vector register is a very big register inside the processor that has many elements associated with it, a vector of elements. Okay? And we have vector arithmetic instructions like this add of v1 plus v2 equals v3 basically takes the first part of v1 plus v2, puts it in the first part of v3, second part of v1 plus v2 puts it into v3, and so on. And the express statement by the programmer is, or the compiler is that each of these is completely independent of the other. Okay, and so now the hardware can be designed many ways. I could have a single adder and just do this sequentially, or I could have 64 of them and do all 64 at once. Okay, so lots of options. The other very interesting thing about vector architectures, and these came, by the way, from mainframes, and things of like Cray ilk and so on, is basically the idea of a load instruction with a stride. And so this load with stride says load starting at address R1 with stride R2. So here's a value in memory that gets loaded into a register. I go to a stride of, say, 2 elements and store that into the register and so on. And so I'm picking out every other element in memory, or every third element, or every 20th element. And why would I do that? I would do that because think about a matrix stored in memory where I want to go down the columns instead of the rows. Well, I want to get every other one, right? Every so many elements. And I can express that directly in a vector machine with a load instruction that has the right stride on it. First, it's very compact for me to express, but even more interesting is the hardware now knows exactly what it's going to need. What is the access pattern? And so it can optimize loads to DRAM without having to have a cache in the middle. So I'll talk about caches in a second, but typically vector processors, when you can express something with vector loads and stores, you don't have a cache in the middle, because the pattern is so regular. Okay? So we can overlap execution of many vector instructions. So suppose we have a machine with 32 elements per vector and 8 lanes. Then I can just do this. So here is a case where I load. So this is all 32 elements of the vector, but I'm going to take them 8 at a time. And here I load 8, and then I simultaneously multiply 8 on the next cycle and do add on the next cycle, and then when the next 8 come in here, and so on. And so I've actually been able to pipeline across the vectors as well, doing only 8 at a time, even though my vectors are 32 size. Okay? This, by the way, is something called chaining that was originally in the Cray 1. And so you can see that with vectors, the hardware implementer has many choices. How many to do at a time, how to chain things together, how big of a vector to make, and so on. And if it turns out your loop has more than, say, 32 elements on this, then you have an outer loop that sequentially does a bunch of things with 32 elements at a time. That's typically called strip mining. Okay. So SIMD is another idea, single instruction, multiple data, where what happens is we have a bunch of elements, and we send the same instruction to each element, and each element gets a different data item. So this is very similar. You can see this is almost a dual to a vector architecture. But typically people think of this as I'm sending the same instruction to lots of independent elements. Rather than the vector cases, I'm sending an instruction to a vector unit. Here it's sort of thought of in a more distributed fashion. They're really duals. And so single instruction, multiple data is the term here. Basically, the central controller broadcasts instructions to multiple processing elements, only requires one controller for the whole array, and only one storage element per for the data or for the instructions, and then individual places for each of the data. And this recently became very popular. You probably all heard of GPUs. In fact, I think you may even be programming GPUs in some part later. And basically, they're essentially modern, updated SIMD architectures where there's a lot of single instructions going on multiple data. Okay? So there's a dual between vector and SIMD. Any questions on this? Okay. Now, there is pseudo-SIMD or poor man SIMD, I don't know, which showed up in a lot of the Intel architectures early on, which said, here's a 32-bit value, but I'm going to think of it as 4 8-bit values. So then when I add x plus y, what I'm going to do is I'm going to individually add x0, y0, x1, y1, and so on in the functional unit by breaking the carry chain. So instead of doing two 32-bit adds and getting a 32-bit result, I'm adding 4 8-bit results together. And getting, okay? And so this was a way to get vector-like or SIMD-like behavior without changing the architecture too much. And there's been many versions of this. You've probably heard of SSE and SSE 2 and 3 and 4. And so there's many versions of this where you break up what would have been a much longer integer into, or floating point, set of floating points into a bunch of individual pieces and do adds and so on them. Okay, and this is kind of like vector processing or SIMD, but it's a lot less flexible because the lengths of the vectors are fixed and the typically where you load out of memory is fixed and so on. Okay. So here is GPU, where this was sort of NVIDIA introduced the GeForce 880 GPU in 2006, and a programming language that went well with it. And GPUs have really been taken off, not just for graphics, but as a more general programming paradigm. And again, very SIMD-like, lots of individual threads all doing the same thing. Okay? And so the idea that the Parlab actually did a lot with, and which was very useful, was taking advantage of the GPU parallelism to do regular, more general kernels that weren't necessarily graphics kernels. Okay. And then typically there's a processor attached to this, or multiple processors. And as I'll show you a little bit at the end of the lecture, there's even some of the newer processors from Intel actually have a GPU and a bunch of cores all in one chip. Okay, and so it's sort of like, let's put both SIMD and large instruction parallelism together in the same chip. Okay, any questions for that? Now, okay. So, at some point, we're telling the programmer to write vectors or VLIW or whatever. We're really kind of pushing our way toward parallelism from the back end. And what else can we do? Well, let's just give up and offer threads. Okay, so that's kind of where the next thing we want to talk about, and this is thread-level parallelism. So up till now, we've been really kind of talking about instruction-level parallelism, parallelism at the instruction level. Thread-level parallelism is really what you get when you introduce threads. So this is the fact ILP is sort of implicit parallel operations within a loop or straight line code, whereas TLP, the programmer explicitly says, here's a thread, here's a thread, here's a thread, run them independent of each other. Okay, and threads can be on a single processor or multiple processors. And this kind of starts running into this concurrency versus parallelism question, so I'm going to bring this up right now. So concurrency is when two tasks can start, run, and complete in overlapping time periods. It doesn't necessarily mean they'll run together, but it does mean suddenly you got to worry about synchronization because those two threads may be interleaved in some complex way. So we really are talking parallelism now where synchronization is an issue and a question. Parallelism is when the tasks are literally running at the same time. So typically, concurrency introduces all the complexity and parallelism gives you some performance back. That's one way to look at this. So when you got something concurrent, you got to think about it. And then hopefully you got some parallelism to make it worth the trouble of having thought about it. Although oftentimes in an operating system, concurrency is really necessary because you have a bunch of things and one thing is waiting on a disk to come back and you want the other thing to run, and so you get interleaving naturally as a way of overlapping I/O and computation. But once you get lots of processors, concurrency is really the beginning of parallelism, and you're hoping that you actually get some advantage from it. So the goal with thread-level parallelism is to use multiple instruction streams to improve throughputs of computers that run many programs or execution time of multi-threaded programs. So either of these. So if you remember that picture I showed you at the beginning of the lecture with the cloud on one end and cars and little things at the other end, at the cloud side, we use threads to really improve the throughput of many requests from different people coming into the same thing. Everyone gets a thread. Down at the low end, we want multi-threading as a way of sort of overlapping parts of an individual computation. Okay? So some common notions of creating threads. So here's the co-begin, co-end idea, where you have a set of jobs and each one of these runs in parallel. Okay? Here's the fork join. This is very common in Unix variants where I say fork and I give job 1 and the argument A1, and what happens is I get a thread ID, and then on the parent I continue to run job 2, and the idea here is that this thread 1 is off, maybe running by itself, hopefully. And then when I get down to the join, what I do with a join is I say, okay, now I'm going to wait here as the parent until thread 1 is done, and now I know they're both done. Okay, so fork join, you have to do explicit synchronization, whereas the co-begin, co-end kind of says, well, everything runs, and then I don't exit co-end until they're all done. Okay? These are just different notions of threads. And then one of my favorite is called a future. So the idea here is you have, you say future of job 1, and you get a result from job 1, and then it may or may not become parallel, but later when you actually use it, what happens is the runtime system makes sure that if job 1 was forked off in parallel somewhere, that it does finish, so I have the actual value. Okay, and so future kind of gives the ability for the runtime system to decide whether making a new thread is a useful thing to do or not. And so there's a lot of models like thread building blocks in Silk and so on where futures are kind of the model underneath there, where things, you sort of give potential parallelism points. That's what this is, and whether it becomes actually parallel or not is up to the runtime system. So threads expressed in the code may or may not turn into independent computations, and this is something you're going to want to really keep in mind for the rest of the afternoon. Okay, it doesn't always make sense to use parallelism, okay, because sometimes more parallelism is just overhead. Just like when we were back, remember out of order execution, that picture I showed you where there was a little bit of black at the bottom of successful stuff and the rest of it was all kind of wasted? There was a case where maybe an 8-order issue was not necessarily useful use of your time. Okay? All right. So let me tell you a little bit about POSIX threads. So POSIX is the portable operating system interface for Unix. This is an attempt that has been somewhat successful over the years to sort of provide a bunch of standards for Unix-like programs to run on top of a variety of different operating systems. Pthreads themselves were part of POSIX 1003.1c. If you have a lot of time someday, you can actually Google POSIX and read through. There's 12 million different versions of the POSIX standard. They've been working on them over the years. They're actually pretty rational standards. They're just not followed by a lot of operating systems, unfortunately. But Pthreads are pretty well followed. Okay, so Pthreads contain support for parallelism, synchronizing, no explicit support for communication. We'll get to communication a little bit later, but the reason there's no explicit support for communication is because shared memory is implicit in this. So if you have many threads, they can all share the same memory blocks, and that's how you communicate. Okay? And a pointer to shared data is passed through a thread, and basically anything that you use for sharing has to be on the heap. It's not for the stacks. Okay? So this is a fairly simple and straightforward model. So typically the way you create a thread is with something like pthread create with a bunch of arguments. Okay? And sort of basically there's the thread ID and a couple of other things here which have to do with arguments. So here's an example. Let me show you. Here's thread ID, thread attributes, thread function, function argument. Notice these are all C pointers to actual structures. So thread ID is something that you'll use to control the thread later. Thread attribute has a bunch of attributes for your thread. And if you put null in there, you get standard attributes. Things like stack size and so on. Thread function is the function to be run. That's the most important part. And then arguments are arguments to be passed. Okay, and here's an example where I have a function say hello. And it just says hello world and returns null. And then in the main, notice what I do. I sort of get an array full of thread IDs. I go through a loop and I create a bunch of threads where I put the thread ID structure here. And the say hello function with no arguments. And so I create 16 threads, and then I join back up with those 16 threads using the thread ID. So notice that's why the thread ID is useful. It gives me synchronization. I can say wait until it's done, and then I return, And what this will do is say hello world 16 times, okay, which is clearly an important first program for all of you to have written. Okay. No, actually, this is actually from 267, one of our graduate courses on parallelism. But it's funny as I'm looking at this thing, I've got a Lionel Richie song going through my brain, which is really bad news. Okay, so shared data in threads in the Pthreads example here. Variables declared outside of main are shared, global variables. Objects allocated on the heap may be shared, as we mentioned before. So basically, globals are shared, and heap objects can be shared. Variables on the stack are private. So if you pass pointers around to these, you can actually get all sorts of problems. So don't do it. Okay? Often done by creating a large thread data structure like this. So here is hello world as a global. And so now when I do pthread create, notice that I'm actually just using the message as an argument here, but now it's as a global. So every one of these threads is sharing the same copy of the hello world string. Okay? By the way, when you actually get to the exercises, you will have plenty of documentation in front of you. So don't worry that if you miss something right now, you're going to fail on Friday. Okay, that's not what's happening here. I'm just trying to give you some examples of how things work. So how do we get loop-level parallelism with this? Well, you can imagine here is sort of two nested loops, and I create a thread for every one of the iterations. Everybody see that? So if n is big, I just created n squared threads. Is this a good idea? Unlikely, right? It's unlikely that this is a good idea because the kind of things you talk about here and that you get to use supercomputers for when you do your exercises, n is big, okay? If n were 1,000 or 1,000,000 or something, you're basically in trouble because you've created so many threads that your whole system's grinding to a halt and nothing's getting done. Okay, and so you need to make sure that whenever you create a thread, it's actually got enough work to justify creating the thread. And this is going to be part of the tuning that you guys get to run into. So a common performance pitfall is too many threads. And the cost of creating a thread can be tens of thousands of cycles on modern architectures. And so you've got to be very careful not to overdo it. And oftentimes you'll do this, you'll have big threads at the top level of loops. When you get to tuning thread usage on multi-core, in fact, we have done examples with custom operating systems where what we do is we try to have one thread per core even. Okay, so there's ideally I only have one thread running per processor or a couple of threads per processor. So if I'm on a 10-core machine, maybe I'll have somewhere between 10 and 20 threads. I don't want 1,000 threads or 1,000,000 threads. Okay, so keep that in mind. So what about thread scheduling? This is another thing to keep in mind. So here I have the main thread is kind of going forward in time, and it forked off a bunch of threads, and A, B, C, D, and so on. But what's interesting is once created, when do the threads run? Don't assume that if you create thread A, then B, then C, then D, then E, that they'll run in anything like that order. This depends on what kind of scheduling is going on. So you've got to be very careful to keep things synchronized. So if thread A is producing something that thread B needs, you need to actually have an explicit synchronization in there to do that. And in many cases, using hints, basically you can play with the thread scheduling such that maybe you can say, well, I want A, C, and E to all run on processor 1 and B and D to run on processor 2. And the reason I want that is because these guys tend to share some data and these guys share some data, and that gives me cache advantages or something. Okay, so there's many options once you've created the threads even to decide where you want to put them. Okay, and as I mentioned earlier, work in the Par Lab and lots of other places have looked at ways of having user-level scheduling for some systems so that once I produce the threads at user level, then I can decide how to schedule them. Otherwise, you're kind of at the mercy of the default scheduler in whatever operating system you use, and so sometimes getting a tuned example program may require a little bit of work on your part to figure out how to make it use the resources best. Okay. So what's multi-threaded execution? Well, in a multitasking operating system, you get the illusion that multiple things happen at the same time. So that would be many threads, but there's only one run queue, and I kind of alternate between them, and that's kind of how, even before we had multi-core, we looked like we had many processes, hundreds of processes running on a Linux box or some other operating system. The reason is that they're being multiplexed on the same CPU in a way that looks like it's multiple threads. Okay? Now, hardware multi-threading is a case where I can take this multitasking view, and possibly on the hardware I can have more than one thread actually running at once. Now, the obvious thing, you might say, well, wait a minute, with multi-core, there's obviously many cores running, and so I could easily have one thread per core running simultaneously, right? But the other idea here is even within a core, you can have more than one thread running. How many people have heard of hyperthreads? Okay, some of you, all right. So if you were to go to try to buy yourself an Intel box or whatever, you'd look and you'd see, well, it supports 2 hyperthreads. I'm going to tell you what that is in a moment, but those are actually 2 threads running simultaneously on the same core. Okay? Hardware multithreading. So when do we switch between threads? So there's some interesting questions here. If we have hardware multithreading and things are actually running at the hardware level, how does it switch? And I'll say a little bit about that. So why don't we, to cap off kind of this part of the lecture and move on to memory systems, ask ourselves, well, what about combining instruction-level parallelism and thread-level parallelism together? If you remember that diagram I showed you with a little bit of black at the bottom, it seems unfortunate that we couldn't use all of that hardware to do more. So if that one thread has got that little bit of black that's making progress, what if we had 2 threads that were sharing the same hardware, and maybe I'd get more progress total between the 2 of them? Does that make sense? So how might we do that? So that would be exploiting TLP and ILP. And so the real question might be, if you're a computer architect, could a processor oriented at instruction-level parallelism somehow benefit from exploiting thread-level parallelism? And the answer is yes. It's actually called simultaneous multithreading. But companies that implement things never like to use the name that the academics came up with. But so Intel called this hyperthreading, but you now know better. You'll know that this is actually simultaneous multithreading. Came out of University of Washington way back when. In fact, it came out of that paper I showed you with the black at the bottom. And so here, remember, there's the idea here is many resources kind of are idle up here because we're waiting on dependencies, and it's really only making good use there. And so here's a very simple schematic of what simultaneous multithreading means. So notice we have cycles, so time is going down in this case, and here I have a bunch of functional units in an out-of-order execution engine, and because of the dependencies, in this case, the yellow slots are the only ones that are busy during this time period. So thread number 1 is this sort of school bus yellow, and on cycle 1, it gets sort of a memory slot and a condition code slot. And on cycle 2, it gets a couple of memory slots and a branch slot and so on. And see all the white in here? That corresponds to kind of wasted time up in here. Okay? Now, what if I have 2 threads and I'm able to shove the 2 threads together into the same pipeline but keep all my accounting right? Okay? Computer architecture is a lot about like accounting. You've got to just keep track of everything, okay? But if I could do that, then what I see here is when the yellow thread can't be using units, then maybe the blue thread can, and I can fill in more spots, and I get higher utilization of the actual overall functional units, okay, by having 2 threads running at the same time, hyperthreading. Now, as you can imagine, it's not always this rosy. So oftentimes, if you put 2 threads together, combined, they don't get individually as much as they would have if they were by themselves, because they're clearly going to conflict occasionally. And so when you put 2 threads together, they run less well. You don't get a factor of 2 speed up. Okay? I mean, you get speed up, but not a factor of 2. And each of the individual ones are likely running a little slower. Okay? Question? So you have to have ultimately at least twice the registers, one for each set for each thread, but it's actually a little more complicated than that. Inside there's a bunch of what are called rename registers. If you think about the The reservation station queues I showed you in the Tomasulo, those are actually registers in many architectures. And so you have to have at least a set of registers for the programmer visible state, and then you have to increase the rename registers inside to really make this work. Now, I don't want to go into this in too much more detail, but the Power 5, which came after the Power 4, actually had simultaneous multi-threading in it. And you can see what they changed. They had to have 2 program counters because you got 2 individual threads running. They had to have a little bit of branch prediction changes because the return stacks are a little different. They had some slightly different instruction buffers. And then the commit logic had to make sure that when you commit results, they go to the right thread when all was said and done. And they did some computation and decided that for this particular architecture, it made sense to have 2 threads, not 4. And the real reason was that when you got to too many threads, then the parallelism didn't pay off and it was all overhead. Okay, and so this was a 2-thread simultaneous multi-threaded machine. And the interesting part is the Power 5 core was about 24% larger than the Power 4 core. So with that 24% extra hardware, we actually got 2 threads running simultaneously. Okay? Questions? All right. Okay.
24% faster?
No, 24% more stuff.
You're saying you're not getting a doubling,
No, but this is not about performance. So in order to have even the potential to do this blue and yellow mix, it took them 24% more stuff for accounting. But you'd get more performance. It wouldn't be twice as fast, but you would get more performance because you had 2 threads that could be running at the same time. So this 24% is a cost factor, not a how much performance you get. That's very dependent on the actual applications you're running. Because, for instance, just imagine if you had a yellow application here that was able to use all of the slots, and you put a blue one in there now, you're going to slow the yellow one down a lot. So it's really dependent on, performance is really dependent on what applications you're running at the same time. There's a question. Yes?
I don't see the difference between simultaneous multi-threading and normal multi-threading.
So the difference between simultaneous multi-threading and normal multi-threading is simultaneous multi-threading is happening inside the pipeline. Normal multi-threading, where you have an operating system, lets one thread run for a while, a timer goes off, you switch that thread state out and put another one in. So you could think of that normal multi-threading in quotes as being not simultaneous because the thread 1 is running or thread 2 is running, whereas in the simultaneous case, they're both running at the same time and the hardware is switching between them. Does that help? Okay. All right. So now we're going to switch gears again. I'm going to stop talking about ILP and TLP. We've sort of mixed them together. So let's talk about the sequential memory system. So the interesting thing is architects like myself and others love to draw log linear scale graphs. Okay, I guess it's sort of, when you get admitted to the architecture groupie status, you have to like log linear graphs. Otherwise, they throw you out of the architecture groupie status. And here's another log linear graph that's kind of interesting, which shows that Joy's law I mentioned earlier with the CPU performance growing at 60% per year for a long time. But at the same time, if you look at the speed of DRAM, it was growing much more slowly. So you basically get a factor of 2 performance improvement in DRAM in 10 years as opposed to 1.5 years. Okay? And so this is the gap, the memory gap. Yeah, question?
I wonder what causes the DRAM not to progress as much compared to the CPU?
So the thing about DRAM is constantly being made larger. So one of the things is DRAM is growing in size, and so that's causing the chips to have more transistors and capacitance on it, which tends to slow things down. And so DRAM tends to be pretty limited by physics in terms of capacitance of long lines and so on in order to have it be a storage element. Whereas in the CPU, you sort of you can isolate where individual pieces are computing, and so you can kind of keep your wires short, and you can get a much faster improvement in performance. And so think of DRAM as more limited by I don't want to say that. I was going to say more limited by physics than the CPU, but that would be kind of misleading to you. But it's sort of DRAM has a tendency to get long capacitances. Okay? And the other thing is that with DRAM, you have to be careful kind of how low the capacitances are made, because if your capacitances get too low, then the DRAM loses its state too quickly and you're refreshing too fast. And so there's a little bit of a, to make good DRAM, it's just kind of slow. It's just kind of where it goes. But the bottom line here, though, is that computer architects have to deal with this because the DRAM is not growing very fast, but the CPU is hungry, and so now we got problems. And so what do? Caching. Okay? I used to joke in computer architecture classes that basically everything in computer architecture is either a pipeline or a cache. Okay? If you can't classify it as a pipeline or a cache, then maybe it doesn't belong in the class. Okay? I was not being entirely correct in that. But the principle of locality basically is that program access tends to be predictable enough that you can do something about that. So programs typically access a relatively small portion of the address space at any given instant at a time. And there's two types of locality that are very useful, temporal locality and spatial locality. So temporal locality says that if I access something now, I'm going to access it soon, in likelihood. Spatial locality says that if I access something, I'm likely to access something close to it in the address space. Okay, so the idea of accessing it soon should be pretty clear to everybody. The spatial locality is really about structures. If you think about the way you program things, you tend to have related pieces of data together in an object or a structure, and if you access one of them, you're likely to access the other one. That's spatial locality. Okay, and basically if programs didn't have some of this type of locality, most of the time, I would say computer architecture wouldn't have gotten anywhere close to where it is now simply because of this gap in the performance of DRAM. And so the last 25, 30 years, hardware relied on locality. Okay? And so let's take a look. Here is an interesting graph that shows kind of memory addresses here and time along this axis. And each dot represents an access to that address space. So here, you see temporal locality is a case where I access the same address over and over again. Spatial locality is where I access a set of addresses that are close to each other. Okay? Everybody with me? This is just bad locality. Okay, let's see how I'm climbing through addresses. There's a case where I'm neither spatial nor local in my behavior. Okay, now you might say, well, wait a minute. If I were to sort of circle something, I'm kind of within a spatial locality piece there, maybe. But if this pattern were to continue indefinitely, it's clearly not very cacheable. And that's kind of the realm where something like a vector architecture would be a better match. Okay? Now, what's the memory hierarchy? We're going to take advantage of the principle of locality to present as much memory as the cheapest technology at the speed of the fastest. And so typically you see there's a memory hierarchy. And here is something that probably none of you have ever seen before, tape. That actually used to be a storage type. Think of this as cloud storage, if you like. Okay? Very big but very slow. And down here are registers, very small but very fast. Okay? And the idea here is that I want my memory system to look like it's got the speed of the fastest thing with the size of the slowest thing. That's our goal. And we do that with caching. Okay, we try to migrate things that are going to benefit from either spatial or temporal locality closer to the register file. And there can be many levels. There can be on-chip caches, other outside caches, etc. Today, on-chip caches are 3 levels at least. Okay, so here is an example of a 2008 chip, just because it's very clear. But notice this is 4 cores. Look at all the third level cache in there. Okay, lots of this chip is devoted to cache. And then actually, if you find regular structures in here too, you've got the first and second level caches as well. Okay, so a lot of this chip is all cache. Why is that? Well, because if it weren't there, this thing would run very poorly. You look at, we've got 32K instruction and 32K data cache, and then at level 2, we've got 1 megabyte of cache in each of these cores. And then out here, we've got 8 megabytes shared among all of them. So caching is pretty important. And you're going to need to optimize your exercises by having some awareness of your cache. That's going to be important. Okay? So terminology, well, hit basically means you grab some, you go looking for some data and it actually appeared in the upper level cache. Okay? So the hit rate is the fraction of time you found it in the upper cache. Hit time is how long it takes you to hit it. Okay, a miss is you went to look for it, it wasn't in the upper level cache, and the miss rate is typically 1 minus hit rate, hopefully. Otherwise, you have some weird probability going on here. Okay, and the miss penalty, however, is a very interesting number. It says if I miss it in this upper level cache, how long does it take me to go down to a lower level and bring it up? Okay, and so if the miss penalty is really, really large, then I could be in trouble even though my hit rate is high. Okay, does that make sense to everybody? So the hit rate, the higher the hit rate, the faster and more likelihood it is that my speed looks like this upper memory. But even if I have a high hit rate and a really long penalty, I may be slow still because those occasional misses basically hold me up for a very long time. Okay, and that very long time can often be, 500 or more easily instruction execution times to go to lower levels to DRAM. Okay, so when you miss in the cache, you can be in big trouble. Think of that as a big lost opportunity if you have to go to DRAM. It's kind of funny. Cray, the king of supercomputers, for years never even put DRAM into his system. Everything was a first level cache because it was fast. I mean, why waste time going slow? So what's the impact of hierarchy on algorithms? I just want to give this is already really old data, but it gives you a great idea. So today, CPU time, which is how fast you're doing, is a function of operations and cache misses, not just operations. So what does this mean to compilers, data structures, and algorithms? Well, here's an example. Quicksort is very fast way to sort when keys fit in memory, and radix sort works well when things don't fit in memory. And so here's a very old paper that kind of took a look at the trade-offs here. And what's kind of interesting is if you purely looked at number of operations and forgot the memory system, what you see here is, okay, what is this? This is time per key here, and this is the number of keys. And what you see here is that as the size gets bigger and bigger, quicksort ends up having a much larger time per key than radix sort. So if you just looked at this, you'd say, well, given that crossover, if I'm down here with small data sizes, I'd use quicksort, and if I'm up here with the big data sizes, I'd use radix sort. Okay, it's reading a graph. Question, yeah?
You can make conditions that determine which kind of sorts can be used. Like, if you detect a size that is small, you use quicksort.
Sure. Yep. The problem is, however, it's not so simple. Because if you actually look at what happens, what you see here is the following. These are the real numbers. So quicksort basically starts out better and is always better than radix sort. Now, why is that? Well, the reason is that when you actually take cache misses into account, radix sort for this set, by the way, this is for a very well-defined set of circumstances, and I'm not going to indicate this would always be the case, but for this particular setup, if you ignore the behavior of the cache, you're in for a completely incorrect conclusion. Question, yeah?
Basically, algorithms that rely heavily on hashing are prone to this kind of like flaw, I guess?
Yeah, so hashing, what does hashing do? Hashing sort of by nature scrambles locality. So, yeah. Now, that's not to say that we should never hash, because hashes are incredibly useful, right? But this is not saying don't hash. It's saying be really careful not to make bad conclusions based on operations only. Always make sure you understand the memory system. All right? And the reason for this is very simple. If you look at what happens is the radix sort just starts cache missing all over the place here. Okay? And so that's why it never recovers. I actually have to show you this data. This is data that Kathy Yellick's group did a number of years ago, and it's a few years ago. Very simple benchmark. Let me see if I can explain this to you. So here is an array Okay, a large array. And what we're going to do is we're going to scan through this array over and over and over again. Okay? And the simplest thing we would do is just read each one of these things, go all the way to the end, come back, read each one of these things, go all the way to the end, come back. Okay, so that's basically just looking at the performance of sequential reads. And we're going to make sure that we look at cases where the total size of the array either does or doesn't fit into the cache. Okay, so obviously if it fits in the cache, first time through it's going to be read in there, and then all the subsequent times are basically just going to be in the cache, and it'll be really fast. On the other hand, if it doesn't fit in the cache at all and I do this, I'm going to keep kicking things out of the cache, and it's just going to show me the speed of the DRAM. That seem simple? Now, here's where things get more interesting. Now, instead, I'm going to basically skip every other word, or every 4 words, or every 8 words, okay? And those will be different examples of things I can do. And here's what is going to happen. So if I imagine what I think will happen is at the low end of stride, so this is really how big is my stride, I'm going to start at the total size of so here's the size, by the way, of the L1 cache. And this is the cache hit time. And what I could imagine is that as the stride increases, so when it's really low, I mean when the stride is close to 1, I'm basically going to be close to my cache hit time. As the stride increases, what's going to happen is I'm going to hit a point where there's no spatial locality left because I'm going every other one, and so every one of these things ends up being closer to a miss. Okay? And then as I get larger and larger stride, what's going to happen is these multiple items are actually going to fit back in the same sets in the cache line at the end. Okay? And so you could imagine that somehow we would expect this behavior as I vary stride. Now, of course, if this total size of this thing is too small, then I'm just going to hit cache time all the time. So I'm assuming that the size of this is big enough that I'm basically always kind of missing in the cache, and the reason I'm not entirely getting the cache hit time here is that I do a miss, but then I get a bunch of spatial locality, and so those are at the cache speed, and then I miss again in spatial locality. Okay, so the expectation is this little hat-shaped thing. Now, wouldn't it be nice if something behaved analytically, because then I could figure out exactly how to write my algorithms, okay? Now, what's funny is, here is the results of this on Sun Ultra 2. And what you see here is nothing quite so simple. Okay, so here is the level 1 cache. Here's the level 2 cache. And here's the memory time. And what you see for different array lengths, okay, and different strides is you actually see that here this guy actually behaves sort of like what we want, but then we get all this really weird behavior in here. Right? And we get different plateaus based on different levels of the memory system. Nothing so simple. Okay? And here is the size of a cache line at L1. Here's the size of the cache line at L2. And you can kind of see where that breakpoint is and so on. So here's the page. So you can go through here and try to identify where all the little plateaus are and why they're there. But it's a little tricky, and it's not quite clean, right? It's complicated. And even better, though, here is the power 3. All right? Figure that one out. Okay, same benchmark. Now, what's the lesson here? The lesson is that the memory system is really complicated in these modern processors. And why are they complicated? Well, because again, the idea is always let's try to make things work as well as we can without causing the programmer to do work. And so these processors have many levels of cache and many levels of prefetching going on. So when you start doing something that looks like you're hitting a regular stride, then some hardware prefetcher goes in and tries to pull the values into the cache, but sometimes that gets in the way of the thing you're trying to do. And then, so the memory system itself is actually interestingly complicated in these modern processors. And so if you're trying to tune your application to work the best on a given architecture, it's challenging. And so what are lessons from this? 1, caches vastly impact performance. 2, the actual performance of a simple program can be a very complicated function of the architecture. And 3, There are common techniques, by the way, for improving cache performance like blocking and tiling and so on, and I'm sure you'll hear some about this. But sometimes they don't quite work as well as you'd expect because of this complexity. Okay? And this led to a word that Jim brought up. I heard him at the very beginning lecture here, which is auto-tuning. And the idea behind auto-tuning is that the system's so complicated that what I got to do is explore the space of possible implementations of a program to find the one that works best on a given architecture. Okay, and so if you can imagine that I have different blockings and tilings and sizes of chunks in my loops and so on and so forth, and I sort of have a space of those things, and what I actually want to do is go through the space and find the one that best matches a given architecture to find the one that's fastest. That's auto-tuning. Okay? All right. Question? We good? All right. So, we're going to change gears here now, if that's okay with people. Do we need another break, or are we good?
Good.
Okay. So what I'm going to switch here to now is explicitly parallel computer architecture. So what we had up till now was the most foray we went into parallelism was threads. But kind of the implication was they were all on the same chip or node, and so sharing with shared memory was reasonably fast. Now we kind of move into this realm where, all right, we're really giving up on giving the programmer, hiding details from the programmer, and now we just have spatial differences in processors spread over time and space, and we have to worry about how to make things work well, and that's parallel computer architecture. And so what is it, just to make sure we're on the same page? A parallel computer is a collection of processing elements that cooperate to solve large problems. And the most important new element here is communication. Okay, it's all about communicating between these possibly separated processors. Okay, and this is where the programmer now starts having to worry about this. They have to worry about things like models of computation. Do we have a PRAM? Probably not, since that's a nice theoretical construct that you can't really build. Maybe we have bulk sequential processing or sequential consistency. Maybe I have to worry about resource allocation, putting my computation next to the right processor. Or how much memory is there? Or do I allocate my memory close to where a computation is going to be? And this really leads to kind of this zoo of possible architectures. What's the trade-off between doing something in hardware and software? There's many options here, and it's not always obvious. And if you look at the vast number of different parallel architectures that have happened over the years, they all take different points in the space between hardware-software trade-offs. And sometimes, as a programmer, you need to know about these. Okay, now what's kind of interesting about the approach that's taken in this class is starting with sort of patterns of parallel computation which are independent of architecture, and then mapping those down into specific architectures. That level of abstraction often helps with this complexity. But my job is to prime you with complexity so you can be impressed when things are simpler, I guess. I don't know. But I want you to know what's really going on in some cases here, okay? So what does a single processor look like? It may be a high-performance general-purpose processor. It may be a SIMD processor or a vector processor. We may have to worry about data access, communication, and synchronization. How do the elements cooperate and communicate? How are data transmitted between processors? What's the abstractions and primitives for cooperation? These are all questions I could ask about an architecture if I were trying to characterize it somewhere. And communication is really the dominant factor, okay? And you must schedule data movement to optimize your performance, okay? Because typically the time to do a flop, floating point operation, is very much less than 1 over the bandwidth, so that's kind of number of items you can get in per unit time, and very much less than the latency. In the dawn of computing time, flops were expensive, communication was cheap. Okay, now I would say flops are cheap, communication's expensive. It's completely different. Okay, it's all about your communication. And so, in fact, if you kind of look here, the energy of communication is often very much greater than the energy of computation. So from an energy standpoint, flops are free, movement ops are not. Okay, and this is kind of an interesting sort of example here where we're looking at picojoules for various pieces of the architecture. And what you see here, and this is sort of now versus 2018 projections, you kind of see the time to do double precision floating point kind of down here. And this is, again, a log scale up here. And if you look at the time to cross the system, notice how there's several orders of magnitude more to cross inside a multi-chip box than there is to pull something out of the register file or do a floating point operation. All right, so that kind of leads you to almost think, well, what I'm going to do is rather than computing something here and communicating it there and using it, maybe I'll just recompute it over there. Maybe it's cheaper to recompute everything than move it. Now, you almost never can do it quite that way, but it leads you to think a little bit about communication and trying to avoid it, which leads to this notion of communication avoiding algorithms, which is something that I think you're going to hear about in one of the lectures, okay? Because communication is just so expensive. Now, let's look here at types of parallelism just here for a moment. So we had superscalar, which we learned about. And that was basically you have several possible issue slots. Time is going down. And for a given thread, what we see is we use as much as we can, and there's sort of wasted slots when we can't. Over here we have simultaneous multi-threading, which is the idea of many threads working on possibly the same pipeline as superscalar. Okay. In the middle we have a couple of versions of multi-threading, which are not quite as complicated as simultaneous multi-threading. And the idea here, for instance, is, I have a bunch of threads, but each thread gets a given cycle. So I do a blue thread, then a red stripy thread, then a yellow thread, then a green thread, then a purple thread, then a blue thread again. So I'm actually just cycling through the threads, each giving them a cycle. Here is coarse-grained multi-threading, where I run for a while, then I switch, and run for a while, then I switch, and I run for a while. Okay, both of these are simpler than simultaneous multi-threading, and they have different trade-offs on how well the hardware is used. This, on the far right, is kind of where we're moving in now, which is, well, if I have the same hardware resources, maybe what I do is have two less complicated processors with less issue slots. Multiprocessor now. Okay? Is everybody with me? So each of these two chunks of hardware now become a separate processor with a slightly lower issue width than the four-way issue here. That's a multiprocessor. Or a multi-core. So what are some programming models here? So a programming model is made up of the languages and libraries that create an abstract view of the machine. We actually have to ask about control, such as how do we create parallelism, what orderings exist between operations, and how do different threads of control synchronize. We have to worry about data, which is what data is private versus shared, how is it logically shared or accessed or communicated, and what sort of synchronization operations can we do, and in particular, what are the atomic operations. Now, I'm going to just touch on some of these, and my goal here, this will be a little like a fire hose approach, but my goal is to give you some of a flavor of all the interesting things that you're going to run into in your programming, okay? And again, don't worry. When you need to know something, there'll be documentation in the various programming things that you're going to do, so not to worry. But so here's a simple programming example. So consider applying a function f to the elements of array A. So here we have A of I is each element, and I'm going to do f of each of those, and then I'm going to sum them up. Okay? Simple. Questions. Where is A? If I have a multiprocessor, is it possible that pieces of A are on each processor? Or are they all somewhere and each processor has to fetch it to them? Okay? What work does each processor do? If they need to coordinate to get the single result, which they do, they have to all talk to each other to get the final sum. How does that happen? Okay? So here, for instance, is a graphics view of what's going on here. So we've got each A element in the array. We apply f to it. That gives us f of A. And then we somehow put everything together to get the sum. And we're going to ask ourselves, what's involved in doing that in parallel? Okay, going with a very simple example. So the first thing is shared memory. Okay, so what is shared memory? Shared memory is a model of programming in which basically there's this huge chunk of memory that shares all the same addresses with a bunch of processors. And if a processor wants to communicate, all it has to do is either read or write from a given address in the shared memory, and another processor can communicate with it by reading or writing by the same address. So basically, we can share data by passing addresses around. That's shared memory. So here, for instance, program's a collection of threads of control. So these are all separate processors. Each thread has a set of private variables, which is its local stack, and then a set of shared variables that are in the shared memory. Okay, and threads communicate implicitly by one thread writing to a memory location and another thread reading. Now notice I said this is implicit communication. Why did I say implicit?
No signaling between processors.
Yeah, so the fact, no signaling, the fact that processor N over here wrote into a given address and processor 0 read from the same address caused the communication to happen, but it's implicit. It's sort of, I used an address. And the thing that's most important to keep out of this is that you don't really know if it's completed yet. How do you know that processor N is done writing? So that's the thing that gets tricky about shared memory. And that's why that leads us to synchronization, which is basically a technique of many possible implementations of figuring out that processor N is already done so that when processor 0 reads it, they get the updated value. That's what synchronization is. So the important part about shared memory is that it's an implicit communication mechanism, and we need synchronization. So how do we use shared memory to do our example here? Let's assume that we have a small number of processors here for the moment, and N is large. And so we decompose it so that each processor is going to get a chunk of A, and we're going to assign N over P numbers to each of P processors. Okay, and here we go. Each processor runs F over its elements and sums things up, and then we combine all the sums together to get the result. Okay, it seems like a simple way to do the communication, and what's nice about it is we just put A in shared memory, and each of the processors just read it. Okay? Now, let's take a look at shared memory code for sum here. So we start out with S equals 0. Thread 1 goes through for, there's only going to be 2 processors, by the way. Thread 1 goes through the first half of them and says S equals S plus F of A of I. Thread 2 does the same thing. And when we're done, we have the answer, right? How many people think this code works? How many people suspect it doesn't because I asked the question? What's wrong here?
There's no suspicion.
Yeah, there's no synchronization here. Okay, and these two uses of S are completely messing each other up. Okay, you're unlikely to get any right answer out of this at all. Okay, and the problem is a race condition on variable S. And a race condition or data race occurs when 2 processors or 2 threads access the same variable, and at least one does a write. Well, here we have both of them doing a write, so we certainly meet this constraint for a race. And these accesses are concurrent and not synchronized. So basically, this code has a data race, and it's unlikely to do the right thing. And I can kind of show you very simply with a 2-element array what the problem is. So here's thread 1 and thread 2. And thread 1 is going to work on one element, thread 2 is going to do the other. And what you see here is assume that that A is 3, 5, F is the square function, and S is 0 initially. And what you think of is that this program ought to get you 34 when you're done, because that's 3 squared plus 5 squared. In fact, you can get 34, 9, or 25. All right, and the reason is, let's look at this. Thread 1 loads A of 1, or A of 0, squares it, it gets 9. Meanwhile, thread 2 loads A of 1, squares it, gets 5. Thread 1 loads S, gets 0. Oops. Thread 2 loads S and gets 0. All right. This guy adds 0 plus 25 to get 25. Perhaps it writes back 25 in S. This guy adds 0 and 9 and gets 9. Writes back 9, and now we're in trouble. All right. So the interleaving here has basically caused our sum to screw up. Okay. All right. So the real question is, what are the atomic operations, okay, of your system? And here they're basically just reads and writes. And you never see half of a number. But plus equals, which is kind of what we started with, is not atomic, and so you don't know, this is never going to produce the right answer. Okay? Now, I don't want to belabor this point. This is clear to everybody? Okay, simple interleaving. So now we can say, what's our improved code? So here, thread 1 does half of them and writes into a local variable, and thread 2 does the other half and writes into a local variable. Okay, and so local S1 and local S2, those are going to be correct because there's no communication going on there, right? But now at the very end, we try to combine them together and we still have the same problem we did with the first example, but now it's much less likely to happen. Now, of course, that's not okay, all right? But we've basically fixed the problem mostly, but what we need to do to finish this off is put some sort of locking around it. Okay, and by putting locking around here, what we've said is we've turned S equal S plus something into an atomic operation by putting locks around it. Okay, and so now only this line or this line get to run at the same time, and we're going to get the right answer out of it. So this is an example where by putting locks in, I can turn something that wasn't atomic, S equal S plus whatever, into an atomic operation and thereby make the program correct. Okay, now can anybody see or explain to me, by the way, why I didn't just use S up here on both cases and just plain put locks around inside the loop? Why did I go to this trouble of doing what I did? What's the reason? Yeah.
Well, then you'd be locking several times, and then you're not really taking advantage of the code.
Yeah, you'd be locking and unlocking all the time, and those locks would be running into each other. You get no parallelism out of this. So by basically splitting out a big chunk of parallelism that's completely independent and then saving my locking for a little bit at the end, I basically get parallelism out of it. Okay? All right. So what about caching? So what's interesting about this is, want high performance for shared memory, you got to use a cache. However, here's shared memory here, here's two processors. What's the problem? Well, the cache reduces latency, so that's great. Okay, but does this work? So if I put a bunch of caches up here and memory down there, what's the problem? It seems like a good idea. It seems like it meets my need for caching I mentioned earlier. Why is this possibly not functional? Yeah. Go ahead.
Cache coherency issues, you have to make sure they're all...
Yeah. So the problem here is cache coherence gets in the way. So this sounds great, but it's broken. All right? Let me just show you. This is hopefully very clear, but we're using some variable u. Processor 1 loads it into its cache. Processor 3 loads it into its cache. Processor 3 writes it. Okay? What happens when processor 1 goes to read? Well, maybe it reads 5 rather than the new 7. Why is that? Well, because it's got an uncached value in its cache. Okay? And what does processor 2 get? Does processor 2 get 5 or 7? Depends. Actually depends on whether processor 3 kicked the 7 back to memory or not, so that when processor 2 gets it, it gets the up-to-date version. So cache coherence gets in the way very quickly. Fortunately, this is not a hardware architecture class other than my lecture, and so you don't have to worry about how to make this work. But the key is that you need to make sure that the cache coherence problem is solved on whatever architecture you've got. And the way to make this work with a bus is you have a cache coherence protocol such that when processor 3 goes to write, it first broadcasts an invalidation that gets rid of the old version of U and all the caches, and so then this write gets put back to memory so that subsequent versions of it read it. Okay, so some sort of invalidation protocol is going to be necessary. Where this comes into play for programmers is if there's a cache coherence protocol underneath and you're doing a lot of writing of the same cache line in different processors, what's got to be happening underneath is pinging back and forth. And that can be very slow. And then where this becomes surprising to people is if you have a cache line that's got 128 elements in it, and you're writing on one part of the cache line and this other processor is writing on the other, you actually cause it to be pinging back and forth even though those two pieces of data are completely not overlapping. And they're overlapping because of the cache mechanism for spatial locality. So these are kind of interesting things that you may want to worry about when you start working on it. Now, of course, cache coherence is not scalable beyond 64 processors, so that's a problem. I'm bringing that number as kind of arbitrary, but it's pretty good. You need something better than a bus, and so what do people do? They use directory cache coherence. And so the idea is you actually have hardware that keeps track of every processor that has a given cached copy so that when you go to do a write, you can invalidate. Okay, and I'm not going to go into this in great detail, but you can imagine something that doesn't require broadcast to keep things coherent, but rather just better accounting to be kept in the directories. Okay. And then finally, cache coherence is not enough. So let me show you this. So everybody look at program 1 and program 2. Processor 1, processor 2. What do you expect to happen here? I start out with everything equal to 0. I write A1, flag equal 1, and this basically says, well, flag equals 0, do nothing, print A. What do I expect to print?
1.
You expect 1. Who said 1? Why? It just seems logical, right? I mean, look, I set A equal to 1, and the flag doesn't get to set to 1 until after A equal 1, and therefore it ought to show up over here. The problem is that intuition is not really guaranteed by hardware. And here you can imagine that if memory is distributed in the right way, that processor 1's write of A may be in a network that gets delayed while the flag equal 1 doesn't, and then processor 3 says, oh, flag turned to 1, and it goes to load A, and it gets the old value of A instead of the new one. All right? So that's a problem. And so basically this is where the memory consistency model comes in, and it basically specifies the constraint in which memory operations can appear to execute with respect to one another. Without it, you can't tell much about how shared memory programs work. And the implications for both the programmer and the system designer is, you basically need to know what your memory model is and know how to synchronize with your memory model. And so the consistency model is really a contract between the programmer and the system. And I want to show you something which is the granddaddy of consistency models, called sequential consistency. And the idea here is that the total order achieved by interleaving accesses from different processes is the same as if everything were running on one processor in interleave. So if you look back here, what we expected to happen here was that processor 1 and processor 2's accesses would actually happen in the order they were specified, and at most there'd be some interleaving between the two, right? Isn't that kind of what people were thinking about? And that's really sequential consistency. Okay? And the other way to look at it is like this little memory switch. You sort of give memory to a given processor at a time, and that also gives you kind of sequential consistency. And there's actually a definition: a multiprocessor is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in some sequential order, and the operations of each individual processor appear in this sequence in the order specified by its program. So basically it says that for any sequential, for any parallel execution where here I store 6 into A and I load that particular 6, that all the arrows of dependency, including forward in time from the processor and the actual communications, can always be put into a total order with a topological sort. That's sequential consistency. That's your intuition. The bottom line, however, is that this is not always available to you, and so you need to be very careful what your consistency model is if you're programming down at the lowest level. Okay. What about synchronization? So all shared memory programs need synchronization. And I mentioned that things are implicit earlier. So mutexes are one option here. So this is kind of the available in Pthreads, and this is the idea that you have a lock, you access shared data, unlock. So that's one possibility. Another is like a barrier, which is all the processors do something, and then they all wait for a barrier, and then they all sort of read values from their neighbors, and then they go on. And so this barrier operation is also one way to synchronize. Sort of everybody does something with no communication, you hit a barrier, they communicate. Okay? So these, both mutexes and barriers, are pthread primitives which are available. Fortunately, a lot of the way that the Paralab tends to think about parallelism doesn't actually require you to be down at this synchronization level. I think we actually make you do something at this synchronization level once just so you know that you don't want to. But somebody's got to be doing it properly underneath. Another thing is transactional memory, which treats memory items actually like miniature transactions, and I'm not going to talk about that right now. So mutexes and POSIX threads. Oops, let's see. So for instance, to create a mutex, you can do this mutex init after you've sort of declared it statically, and then you can do mutex lock and unlock. Okay, so correctness pitfalls with locks. You have too many locks. So here is S plus 1 stored back. This is a completely useless use of locks because I'm not actually putting locks around the critical section that I want. See, I'm not actually putting in a lock around S equal S plus 1. Instead, I'm doing a lock around grabbing S and releasing it, then adding 1, and then putting a lock on my storing back. That's not going to help me. Okay. All right. And the other one is that you can get into deadlock. So here's something where I lock A, then I lock B. Here's a case where I lock B, then I lock A. So I can actually get in a deadlock. Okay, so these are other fun things. Other performance pitfalls is I lock for too long. I lock, I run to the last digit of pi, I unlock. Okay, you can imagine the problem with that is perhaps somebody else is waiting a while. Okay, and so you got to decide how big your lock regions are. Okay, and finally barriers, as I mentioned, are another option. Okay, so barriers and POSIX threads. Basically, you can do a pthread barrier init with the number of processors, and then you can do a wait, and it'll automatically decrement properly and wait for it. Okay. So I'm going to briefly, I don't want to talk about this. So I want to talk about message passing. So the other interesting thing here is the second model would be message passing. And so notice this is a little different from shared memory. Here we have a processor talking across a network with other processors, and there is no shared memory, and all I'm doing is putting messages together to communicate. So I send a message to somebody, I receive a message from somebody. So a program consists of a collection of named processes, often fixed at startup time, and there's no shared data whatsoever except that which is sent by messages. Processes communicate by explicit send and receive pairs. And MPI is a very common version used. Okay, and I think we may do some MPI here. And the idea here is that processor N might send a message, processor 1 might receive, and as a result, the communication happens. So in this case, unlike shared memory, the communication's explicit. Okay, because I know when I received a message. Okay, so notice that what's different here than shared memory is when processor N sends something and I receive it, then I know the processor N has sent it. Okay, so this is a combination of both communication and synchronization in a single memory packet. So that's kind of nice. And so if we want to do something here, for instance, to compute A of 1 plus A of 2 on each processor, what I need to do is it may be the fact that processor 1 has A of 1 and processor 2 has A of 2. What happens here is, well, processor 1 sends its value over to processor 2. Processor 2 sends its value to processor 1, and now they can both receive and then do the sum. So what could happen here? Well, if this send-receive actually requires some sort of communication channel to be set up, then it's possible that this send blocks waiting for that receive, and this receive blocks waiting for that send, and we basically make no progress. Okay? And so we can actually swap them. Now, fortunately, most systems... Actually, I won't say that. You need to know when you're using explicit message passing whether you have something where an explicit communication has to be set up, or more likely where it's just queuing. So you send something off into the ether, into the network, and then you receive from the network. Okay, and that's more likely for MPI. Yes, go ahead.
When would this system be more useful than this? Because the shared memory seems so much more simpler, and I just like it seems a lot nicer. And this seems more like for distributed computing where you don't really have shared memory because each computer talks to it, then this makes sense. Like, why don't you use at the processor level?
So I would say, why use message passing? So depending on your type of application, some applications are naturally message passing in nature. For instance, take an event-driven simulator. So it's very natural to be sending an event off. or take an operating system, very natural to do explicit message passing. Okay? Now, the second thing I'm going to mention is that cache coherence. I sort of wove my hands there and said, well, you just put a directory in and so on. But when you are interested in scaling to large numbers of processors, it gets very expensive, including energy expensive. Now, I've actually heard from Intel researchers now and then saying, well, in the future, Intel's thinking that they may remove cache coherence entirely because it's too expensive from an energy standpoint. What's nice about message passing is you're explicitly coordinating everything. You know exactly what's going where. And as a result, there's no kind of wasted communication. Okay, in shared memory, take that example where I write on two processors and they just happen to be sharing a cache line by accident. There's a bunch of wasted communication underneath there that I don't know about, and I've just burned a bunch of energy and performance for no good reason. And that's in order to give me the illusion that there's this infinitely fast memory thing out there that I can use. So I think the real answer here is that if you can cast something as a message passing interface, and if the overheads of marshalling and putting packets together aren't excessive, then it might be better to do message passing, even on a shared memory machine. Okay, now you probably didn't expect me to say that. Now MPI has become kind of the de facto standard for parallel computing using message passing. So oftentimes if you want to write a program that you think you can run on all the big machine supercomputers in various parts of the country, you might write an MPI version. And it's really literally a message passing protocol like this. So I go in a loop and I send off a bunch of buffers of strings that say hello, whatever. And on the other side, I then receive from a bunch of people and I print out the results. And so MPI is a whole standard. You guys can Google it. You may actually even be using it today or tomorrow. But it's got many options, okay, having to do with these questions of blocking channels and so on, and what do I do on the other side? Do I cause interrupts and so on? So the pros and cons of standards like this is MPI actually was good because it created a standard finally in the HPC community, which gave some level of portability, and it's the least common denominator building on things of mid-'80s technology. Unfortunately, it's a very old standard now, and it's got a lot of overheads, and so it may end up causing, it's a lot more performance hungry than, say, if you were to code everything by hand. But it's a good way to get portability. So, yeah, go ahead. Question. Yeah, so oftentimes MPI runs over the best underlying system available. So in a really big installation, you might have a bunch of nodes, which are things in a box and maybe in a rack, in which case maybe it'll run over a specialized high-performance network that's available, but then between those might be TCP/IP or something else. And so it can actually run over several different network media. It doesn't have to be TCP. Yes. It's sort of intended to be an abstraction of message passing. So what are some details here? All the data layouts handled by software for message passing. Can't retrieve remote data except with the message request reply. And often message passing code is produced by the compiler. So there's a lot of work up at LBL on UPC and a few other message passing targets that actually come out of compilers. So oftentimes you don't even have to do the message passing yourself. It's done for you. You're programming in a way you think is shared memory, but it's actually producing messages underneath. So potentially there's high software overhead. So early machines had to invoke operating system for every message. And then there was a bunch of work on user-level message passing machines. I did some of that at MIT and others to try to make the messages really cheap. Now, unfortunately, those machines aren't that common, and so usually you end up with some sort of either interrupt at the other side for messaging, or there's a coprocessor whose sole job it is to handle the message passing, in which case it's cheaper. But this also led to what's called the active message abstraction, which is a type of message passing in which one of the things that's in the message is a handler to run on the other side. And it turns out active messages are potentially very efficient on the right architecture. And so it's a good compiler target in often cases. Sorry. So let me just briefly mention this idea of a dedicated message processor. So here's a case where there's a special processor whose sole job is to handle sending messages back and forth. And in that case, the user code sends either a system call or something to the or user level message to the message processor, which then takes the trouble to send it to the other side, in which case it's then forwarded to the user. So oftentimes there's message hardware that's available. Here's a machine that I put together once upon a time, where to send a message, the user level code just put a bunch of descriptions in user level registers and then did a launch, and it went off entirely at user level. And then at the other side, there was a special user level interrupt that actually happened entirely at user level as well. And so you can get very cheap message send and receive on the right hardware. Unfortunately, this kind of thing's not often available. So one last thing I wanted to mention here is the danger of direct access to networks is the fetch deadlock problem. So here's a case where this processor wants to send into the network, but the whole path between here and this other processor is full of messages and blocked. And this processor can't pull a message off of there because it's trying to send a message. And as you can see, you have a loop, so you've got a deadlock. Okay, and so any system that gives the user direct access to the network has to worry about this deadlock problem. And typically the way you do it is by providing multiple logical networks, so that there's a send and a receive network, or sometimes many of them, so that you don't have any of these loops. Okay, which is better? Shared memory or message passing? Well, it depends on the program. Both are, for lack of misusing words here, communication Turing complete. You can build a shared memory system out of messages. You can build a message passing system out of shared memory. Okay, clearly, think about it, it's not hard. The question is really what's more efficient on the given architecture. So the advantages of shared memory is implicit communication. So a single load or store communicates. That's very efficient. But now you're stuck with synchronizing. And your cache gets used. So disadvantage, it's complex to build cache coherent systems in a way that scales well, requires synchronization operations, very hard to control data placement. Okay, because you don't really know what the caches are doing. It's all happening under the covers. The advantages of message passing, it's explicit communication. There's no synchronization. It's easier to control data placement. The disadvantages are typically the overheads can be high to get in and out of the actual message interface. Often you have to marshal your data into the message, so you have to put it in a format that's transmittable. And then you start worrying about whether you have interrupts or polling at the other side. So my bottom line is I actually think both are appropriate in different circumstances.
Isn't there more disadvantages of message passing?
Well, it depends a lot on the architecture. I mean, I will say that there are many cases where there just isn't shared memory available, and then message passing is the right way to go. But even when there are both available, when you're inside a given box or a rack, it's possible that you don't have as many message drops and whatever, and so some of those disadvantages go away. And the advantages of directly placing your data are much higher than the disadvantages, and you get much more performance than you would with shared memory. So it really depends on circumstances.
Yeah, I mean, the reason I say that is I'm on a project where we're not using this particular technology, but we're using commodity hardware.
Right.
And we're finding that we're actually losing data between racks, dropping messages.
Well, you do have to have some layer of retry underneath. I mean, whether going to the full algorithms of TCP/IP may not be the right thing with inside a rack. You may want to have more specialized detection, or you could use forward error correction, where you actually put correction in the picture. So there are many ways to fix those kind of things. So I think it's a 6.5 of one, half a baker's dozen of the other as to which one's better. So very quickly, and then I notice we have an announcement or something, or? Oh, okay. So any other questions about this message passing versus shared memory question? So in message passing, you don't have to worry about memory model because you know exactly how the ordering of updates are going to appear. I mean, you're event driven. In shared memory, there's the implicit aspect of it's nice because it caches automatically and you get performance of a single load or store instruction makes a communication. So I think it really depends on circumstances as to which one's better. And it's good to have both of them kind of in your wheelhouse as to what you are thinking about. Okay? Now, if you give me just a few moments here, I can show you some interesting zoo of machines. I just want to show you a couple of pictures. So MIMD machines, multiple instruction, multiple data, is multiple instruction streams, program counters, etc. This is kind of the most general parallelism you can imagine where there's just a bunch of individual processors and each of them are doing their own thing. Okay, think of that as in contrast to SIMD earlier where there's a single instruction, multiple data. Here we have multiple instruction, multiple data. Every processor is doing its own thing. And that's the most general type of parallelism. And when the processors are basically confined to a single chip, you end up with a multi-core processor. Okay. I remember when I was designing parallel machines and every processor was a board, and then people would say, well, someday we'll be able to put multiple processors on a chip. And it's like, yeah, someday. But, when you put multiple things on a chip, how much different is it from multiple boards? Well, there's different communication overheads. Things are much cheaper to get between processors on a chip than on a board. So while it's in principle the same thing, there's interesting trade-offs in your communication performance there, always to know or always to think about. So shared memory is one way communicating through memory. You can either have no global cache coherence or global cache coherence. Message passing, you can have explicit sends. And for most machines, shared memory is actually built on top of message passing. Surprise, right? So you build a message passing network and the shared memory is just some additional hardware that sends and receives messages on top of it. Okay, that's just the way you'd build it. Unless you were building a bus-based cache coherent multiprocessor, and there aren't very many of those anymore. Well, there's some, but not as many as more general networks. So here's some examples. Symmetric multiprocessor with a bus. Okay, that's what you might have inside a single chip now, although that's less likely. Here is a shared memory machine with directory cache coherence, and where each processor has a chunk of the memory and a processor, and you have some general mesh network on top. Okay, and this is going to have something like that directory cache coherence I mentioned earlier. If there's shared memory, if there's only message passing, that's easy. A cluster. Okay, a cluster is a shared memory machine, right? Or no, maybe it's a message passing machine. Well, it depends on, do you give a shared memory abstraction on top of messages? Clearly, the underlying communication substrate's TCP/IP, but you've seen people build both shared memory-ish machines or message passing machines on top of this. So the Cray T3E, here's an example of a nice one with a three-dimensional mesh network and a bunch of processors in it. Okay. Cray also had another version of this where you could choose kind of what you wanted to plug together. So every processor node could be a little different and you could put a bunch of them together. SGI Origin was one of the first commercial directory cache coherence machines from SGI way back when. That was kind of nice. Here was the machine I built. I have to show baby pictures from way back when. So this was actually a cache coherent shared memory and message passing machine. Both were given to the programmer. And every board was a separate processor way back when. Let's see, the last thing, and here's a good one that was built at MIT once upon a time called the J machine. So this was a message passing only machine. And this was 1,024 processors in a three-dimensional network. And we used to like to think of this, we called this the rocket launcher. But this is the way it actually looked. So that was an old message passing machine way back when. So here, just my last two slides here. Here's some modern, very modern chips. So this is an Intel Gulftown, 6 cores, shared L3 cache for each group of 3, memory controller, and so on. Here's an AMD Opteron. Just so you know, we're basically in the 4 to 16 core per socket kind of realm these days. pretty much for the normal processors, and multi-socket configurations basically give you more processors. Here's a closer look at Sandy Bridge, just to give you some counts. So notice that we're talking about up to, for instance, with 8 cores, we can get 2.27 billion transistors, and general ring bus and a GPU all on the same chip. So there you go. Lots of the things I've talked about today. Each one of these cores does out-of-order execution, as I mentioned as well. Okay, I think that's going to be enough. So in conclusion, and the last thing is the typical GPUs basically are very interesting. Lots of SIMD possibilities, and I think you'll get a chance to do GPUs later. Yes. Good. So in conclusion, I told you about uniprocessor parallelism, pipelining, superscalar, out-of-order execution, vector processing, SIMD, pseudo-SIMD. Boy, the architects pulled out all stops because we wanted to hide parallelism from lowly programmers. Okay, unfortunately, it didn't work out too well. Okay, and so then we introduced multi-threading, which is multiple independent threads executing on the same processor. And then we had to accept the fact that we're running into problems. The memory system was slow, so we had to do lots of caching and prefetching, which put complexity in. And then finally, shared memory, message passing. Explicit threading was really the name of the game, which is where this class is today. And it's basically the fact that, look, multiprocessor architects became the coin of the realm because there's just no way to hide the fact that there needs to be parallelism from the programmer because the hardware just can't possibly do enough. And so that's where explicit parallelism comes into play, and that's where this class is about. And I'm sorry I went over 7 minutes, but hopefully you have a great rest of the class, and good luck. And I'll be up here for some... I'll stick around.